Okay, so we start the next lecture, and we were talking about this expression G is equal to G0 plus RT ln activity. Now, before we proceed, we should learn a few things beforehand, because it's very, very important to learn. There are certain thermodynamic terms with which you should get quickly associated. One of the terms that is important is called the system. A thermodynamic system. Now, a thermodynamic system essentially is any part of the universe which you think should be analyzed thermodynamically. It could be the whole earth, it could be the crust, it could be a rock in the crust, it could be a mineral in the crust, it could be an orthopyroxene MgFe whole twice Si2O6. It also could be a one-sided orthopyroxene. Now that system needs to be defined by the user. Have you understood? It depends on you what is the end boundary of your system. You could consider the blackboard as a system, and then everything around it is a part of the environment. Okay? It's a part of the environment. So that is what is called a thermodynamic system. It could be a rock, which would mean the assembly of rocks, assembly of minerals. Say, for example, if you have a layered rock like in gneisses, so you have dark bands and light-colored bands. So you may consider the banded rock as a whole as a system, or even you could consider individual dark layers and individual light-colored layers are two separate systems. So it all depends on you. There are three types of systems, as you all know. One is called the closed system, isolated system. An isolated system is one which does not exchange mass or energy with its surroundings. That's an isolated system. That means the system as a whole has got no connection with the surroundings across the system surrounding boundary. But then you can have another type of system called a closed system. What is that? Where the system can exchange energy with the surroundings, but not mass. So essentially the composition of the system remains same. And you can have an open system where the system exchanges both mass and energy with the surroundings. So you have isolated system, which is not used in geological system that we are talking. You have closed systems and open systems. Many of us deal with closed systems, but almost everyone knows that any system is not perfectly closed. Most systems are open to some degree, so that the mass and energy across the crust-mantle interface, system surrounding interface can change. So closed system is a very idealized system, but you could apply it to nature, because if you open up everything, then there are too many variables changing. It is difficult to model it. But there are attempts, there have been attempts to model open system. There's no doubt about it. But yeah, closed system is a good way to learn it. Like, you know, it is very similar to, say, the Euclidean geometry, which essentially deals with planes. That you have a triangle that lies on a plane, a square that lies on a plane. And when we grew up, we knew that, okay, There is nothing but a plane, it's a part of a curved surface. And so then we moved over to what is called solid geometry. So it's a similar thing. To learn thermodynamics, it's better to learn it in a closed system rather than opening it up and making the equations complex. We need to understand the basics. So that's much about the system. The second is what is called the phase. It's called a phase. Now typically, phases, a system may contain one or more phases. Say for example, if you take quartzite, pure quartzite, then that quartzite, that system quartzite, contains only quartz. Have you understood? If you put it at high pressure, it becomes quesite or stishovite. But you would consider a quartz to be a monomineralic system. But you can have multimineralic systems where the rock contains several minerals. But how do you make a thermodynamic definition? Well, I will always ask you to read the book. Generally, they have each phase in a system has a distinct physical property and chemical characteristic that sets it apart from another phase. So it should have certain physical properties and certain chemical characteristics. So it can have a definitive boundary by which you can separate it from the other phase. Say you have all gone to the microscope. So if you have muscovite and garnet, say for example, you know garnet has certain physical properties and certain chemical compositions that sets it apart from mica, which has a different characteristics and different compositions. So mostly minerals are considered to be phases in the system that we are talking about. There is a more complicated issue which we will try and come back at some point of time, is fluids. Now most phases, as you can see, when you look at a thin section of a rock, most phases you can see. But there is say for example, you have muscovite in your rock. That means muscovite had an OH2 radical. So has amphibole. Chlorite has an OH8 radical. So these are structurally held water, which tells you that there was a fluid in equilibrium. But you look at the section and you don't see the fluid. So what do you do with the fluid? It's a more tricky way to deal it, but take it from me, we consider the fluid as a phase. Although I can't see its physical properties, I can only assume that it was there, and its composition also I do not know. But I know that it was there. Otherwise, you would not have muscovite in the rock, or amphibole in the rock, or chlorite in the rock, or kaolinite in the rock, or prainite, or pumperite. So that is a little slightly difficult. We will see how we deal with it. But yes, fluids are considered to be phases, and you can have in fluids what is called fluid absent situation. Absent does not mean that there is no fluid. Fluid absent means something else thermodynamically, and fluid present situations mean something differently. I don't know whether we can go into that details at the moment, but let's get on with the class. This is already a compressed semester, and I'm trying best to at least teach you whatever is necessary. If we find time, I will definitely tell you a little bit about classic metamorphosis. So, for example, then we have there are what is called components. Now that's a very, very tricky thing, components. Now, thermodynamically, there are two types of components. One is called system component, and the other one is called phase. Something is called a system compounds, something is called a phase component. I will talk to you about phase component first. Now, say for example, you have the mineral Mg, Fe whole twice SiO4. Now that is the formula of a normal olivine. So olivine is the phase. It is the phase. It's not the component. Olivine is the phase because it has certain, optical characters. It has certain physical characters which are very distinctive, and it has a composition by which you can quickly identify this mineral is olivine. So olivine is a phase, but its composition of the olivine can vary. So as you all know, normal olivines are divided into two parts, Mg2SiO4 and Fe2SiO4. And Mg2SiO4 is called forsterite and Fe2SiO4 is called thiolite. And if you mark here, so you can mix up magnesium and iron in any proportion. We will do the thermodynamics later when we come to orthopyroxene. But you can see this is an octahedral position, this is an octahedral position, this is a tetrahedral position, and this is a tetrahedral position. These are the two octahedral positions. So magnesium and iron, the composition of olivine lies between Mg2SiO4 and Fe2SiO4. So olivine is bound by two end-member phase components. Have you understood? Two end-member phase components. And you can form a solution of it to give you the composition of any olivine that you want. Now, forsterite and thiolite are called phase components. So here, olivine is the phase, and forsterite and thiolite are the phase components, are the components of that phase, which is phase component. So say for example, another example, Mg3 or MgFeCaMn3Al2Si3O12. This is the formula for a garnet. Typical, there can be more complications. I'm avoiding the complications at the moment. So you can have Mg3Al2Si3O12, Fe3Al2Si3O12, Ca3Al2Si3O12, and Mn3Al2SiO4. That means you have pyro, almandine, grossular, spessartine, garnets, 4 compounds. So garnet is the phase, and its composition, a simple garnet, its composition can be put into a 4 end-member space, 4 component space. And these, each of them, Mg3Al2Si3O12, Fe3Al2Si3O12, each of them are phase components. But say for example, quartz has the formula SiO2. It is a one component. So the composition of the phase and the composition of its component SiO2 is the same. So that is what is called a phase component. That means, in speaking about it analytically, phase components are the number of end-member formulas that can describe the chemical variability of a phase. The chemical variability of a phase. That is what is called system components. phase components. Now we come to the other part, which is, we call it the system components. Now this is a slightly trickier one. We will talk about system components. Now, I do not know if you know this formula, although we will have to know by heart once we are in this business. It's called F is equal to C minus P plus 2. I'm sure all of you have heard this formula. This is called Gibbs phase rule. Gibbs phase rule. I'm not going into the details now. If you get the chance, we'll go into very great details. F is called the degree of freedom. This C here is system component. This C here is system component, not phase component. P is the number of phases, like we discussed before, is the number of phases. 2 comes in because of pressure and temperature as the right. Now we are talking of this C, which is essentially called the system. Now, definition-wise, system component is the minimum number of components that describe the chemical variability of the system, not the phase. Have you understood? So C is the minimum number of components that describe the chemical variability of the system, which includes multiple phases. Let us see how this works. Say, for example, I take a quartzite. Absolutely just quartzite, with nothing else except quartz. Its formula is SiO2. So, this is a rock which has one phase, quartz. The composition of quartz is SiO2. So the system component here is 1. System component is 1. What is it? SiO2. SiO2 is a component, there is nothing else, and you can describe the composition of your quartzite made of pure quartz only as one phase, one component system. So it's one phase quartz, one component C, one component C. So 1 minus 1, your degree of variable should be 2. We will talk about that later. But what I'm trying to say is, this is very crucial. This is the minimum number of components. Underline minimum. Get it in your head. Minimum number of components that describe the chemical variability of a system. And your system is a rock. The rock contains multiple minerals. Okay, we have talked about quartzite. Fine enough. Now let's say we have SiO2, Al2. Now what happens? What are the possible minerals? There can be many possible minerals. So say for example, you will have SiO2 means the quartz and its polymorphs, which means there are many polymorphs of quartz. So SiO2 and Al2O3, the chemical formula of Al2O3 is corundum. The name of the crystalline form of the mineral that is Al2O3 is corundum. Now let's say I have a rock, which is a quartz corundum rock. Have you understood? Quartz corundum rock. Quartz corundum. That means the number of phases are quartz and corundum. Right? Corundum has the formula Al2O3. Quartz has the formula SiO2. So we can write possible combination of elements as SiAlO, SiO2, Al2O3. Which do we take? Which of these two things we accept as system compounds? Both are all right. If I take quartz, then if I take the formula is SiO2. So Si plus 2O is equal to SiO2. Similarly, corundum, which is Al2O3, I can write 2Al plus 3O. Al2O3. But also I can take SiO2 and Al2O3. So for quartz, it is 1 into SiO2 plus 0 into Al2O3 to make it quartz. And for corundum, it is 0 into SiO2 plus 1 into Al2O3. That's corundum. So which one should I take? I will take this. Why? Because this C here is equal to 2C here is equal to 3. The minimum number of components, minimum. So that's it. This is the number of components of the system. Okay. Now let's say I have a rock which contains only silver. Say only silver. Okay, let me write it a little differently. Let me write silver. Now, how will you express its composition? You can take SiAlO. You can take SiO2, Al2O3. Or you could take Al2SiO5. Here C equal to 1, here C equal to 2, here C equal to 3. The number of components here becomes 3, here it's 2, here it's 1. So what is C here? The minimum number of components. It's Al2SiO5. So again, have you understood? So again what we have to look at the minimum number of components that can describe the composition here of sillimanite, which is Al2. No, sometimes, not sometimes, almost always. Sillimanite, if you analyze it using electron microprobe, you will see the formula is not Al2SiO5, but Al, Fe SiO5. This iron is trivalent. This iron is trivalent. What happens? Ferric iron substitutes for aluminium. So what happens is, this sillimanite now can be written in terms of Al2SiO5 and Fe2SiO5, and this is trivalent. So now it has two phase components. If it was pure, it would have been one phase component. So if you have sillimanite and it contains ferric iron, then the number of system components will also be Al2SiO5 and Fe2SiO5. So the component is not one, the component is two, system component is two, which is the same as the phase component. Let's take one more example. I think we can leave it at this. So what is important for you to understand here is that you have system, phases, phase component, system components. These are the four parameters that is important. Phase components are those that describe the chemical variability of a phase. System components are those that describe the chemical variability of a system which is composed of one or multiple phases. Now when I write this formula, G is equal to G0 plus RT-ln activity A, I have not referred to something. Normally, if I write X phosphorite olivine, this means in an olivine, this is the amount of X phosphorite, or some people would still write XmG olivine. Have you understood? Here, or in a general case, Xi alpha. This means that I am talking of mole fraction of a component I in a phase alpha. You can also write a phase beta. You can write a phase zeta. That's unimportant. But what is important to realize that when you talk of thermodynamic functions, the subscript refers to the component and the superscript refers to the phase. So the superscript refers to the phase, the subscript refers to the phase component. If you do this, then this equation would become Gi phi is equal to Gi 0 phi plus RT ln activity I phi. Now you see there is a distinct change now. This is flat. You don't understand what you're talking about. What is here is free energy of a component in a phase. Free energy of a component in a phase is equal to the free energy of that component in the phase if it was pure plus RT ln activity of the component in the phase. Have you understood? And as I told you before, this is the energy of impurity. This is the energy of purity. And this is the total algebraic addition of the total free energy of a phase component. Have you understood? This is free energy of a component in a phase. I will write to you so that you get the familiarity. G albite in plagioclase is equal to G albite plagio 0 into plagioclase plus RT ln activity of albite in plagioclase. Do you get the point here? You must remember that you are talking of a component in a phase. Phase component in a phase. That is what is a phase component. So this type of a writing is not correct. This is a better way of writing it. But why I wrote this way? For your mind to get focused into what free energy, what are you talking? Is it the free energy of a phase or a phase component? This equation is of a phase component, not of a phase. And there are further corrections to this diagram. Now you see all equations, thermodynamic equations, are equations of state. That means they depend on the initial state and the final state, the pressure temperature condition from an initial state to a final state. It is unimportant which path you took for going from an initial stage to a final stage. So all your thermodynamic parameters refer to a particular pressure temperature condition. So this equation, if you write it even correctly or more precisely, this equation will be GI phi pressure temperature. Have you understood it? Free energy of a component in a phase at a particular pressure temperature is equal to GI 0 phi pressure temperature plus RT ln activity of I phi pressure temperature. They all represent a particular thermal state of the system. If you change any of these variables at the top, the numerical values would change. So this is a very generalized form. This one includes the phase of the phase component. This includes the thermodynamic state of the reaction in terms of pressure and temperature. Again, the meaning of it is the same. Say, for example, what does this term mean? This means free energy of I at a particular pressure temperature for the phase to have been pure. Whereas this is the free energy of a component I in a phase phi at equilibrium pressure temperature, not pure. Have you understood? And this is the impurity. This is the impurity. So if you know this, what you are talking about, in terms of phase components, in terms of phase, in terms of thermal state of the system, and if you write this then knowing it, then it's okay. Some people, I am not in physical class now, I am talking one way, which is quite boring for me. Many students, if you ask them, they will say, this means standard state. It's not. G0 means standard state. It's not. G0 means pure phase component. A particular phase component, the free energy of a phase component, that the component is pure. That's what it means. It has nothing to do with 25 degrees centigrade and 1 of those things. No. In fact, it qualifies for a particular pressure temperature condition on which you are observing the system. Now, if you have understood this, then we go over to a slightly different direction from here. Now we talk of the term activity, A. And this, I told you, is X into gamma. Now with our knowledge, we write this is more correct. I have not added pressure and temperature. I am assuming that, okay, we talk of it at a particular pressure temperature. It's still wrong unless you put in the thermal state. But we understand we can write at PT conditions. So whatever the PT conditions is, this is the equation. Activity is equal to X into gamma. Let's take a binary system. A binary system like we have, say for example, olivine phosphorite, something like this. Firelight and phosphorite. Firelight and phosphorite. A binary system. Garnet example was force chemical composition. So this was a quaternary system. It can be made bigger if we add chromium to replace aluminium. If we take ferric iron to replace aluminium, then it becomes an even more complex system, as is the case for mantle gardens. Now, none of these terms have any unit. They are dimensional results. So if we draw a diagram, which is X and A, where A varies from 0 to 1 and X varies from 0 to 1, and I draw a line here. These online classes, I used to draw good straight lines. Looks like I have lost the habit somewhere. Okay. At this point, this is A is equal to X. Remember, this is xi phi, I phi, and so on. So this line, 45-degree angle, A is equal to X. A is equal to X. That means gamma is equal to 1. Such systems where gamma is equal to 1 are called ideal solutions. Are called ideal solutions. We will go into them in greater detail in the next class. A is equal to X, which means gamma is equal to 1. These are called ideal solutions. Now, but AX relationships are not that simple. It can become very complicated. So normally what happens, you can have a situation like this. You can have a situation like this. Here you can see A is greater than X. Can you see that? For a particular X value, A is greater than X. So if A is greater than X, then gamma should be what? Gamma should be greater than 1. Yes or no? If A is greater than X, then gamma should be greater than 1. If this is so, then this is called positive deviation from ideality. This is called positive deviation from ideality. Obviously, ideality is here. It's a positive deviation from ideality where A is greater than X or gamma is greater than 1. And you can have situations where it's like that. And here, A is less than X. So here, A is less than X, and therefore gamma is less than 1. So this is called negative deviation from ideality. This is called negative deviation from ideality. In either case, they are called non-ideal solutions. These are called non-ideal solutions. And this is a case where it's called ideal solution. We will talk how non-ideal solutions become ideal solutions, etc. We will talk about that in next few classes. But for the moment, just certain informations. So, if gamma is not equal to 1, these are called non-ideal solutions. And if gamma is equal to 1, these are called ideal solutions. This is related to a term we will understand, excess free energy of mixing. We will come to that after 1 or 2 classes, I guess. And I will give you PDFs of the derivation so that you can try, and I will tell you where to read it from so that you get an idea. Somehow, for many of you, these all things might be a little new as of now. It will become newer as we go further ahead. So we have to be very alert as to what we are doing. Now a little tricky problem is here. It is a little tricky problem. Here you see the condition, if we make it small, x, oh, sorry, this was a mistake. X, for the case x tends to 0. If we take x tends to 0, what does this mean? That the mole fraction of a phase component is tending to 0. Means what? For a binary solution, if one component is tending to 0, then the other component is becoming almost mono, has only the other component is almost tending to 1. So, here you see when x tends to 0, then you can see from the convergence of the graph, gamma tends to 1. X tends to 0, tending, gamma tends to 1. That means, whether it is ideal solution or non-ideal solution, if we take the case of a solution where a particular component is tending to 0, this is technically called infinite dilution. Infinite dilution. X, mole fraction tending to 0 means it's a case of infinite dilution. That means the other components are almost pure. In that case, gamma, the activity coefficient, is equal to 1. This has a big usage in geochemistry. You know, in geochemistry, you have heard a term called partition coefficient. Crystal melt partition coefficient. Have you not heard? Say potassium, say for example, partition coefficient of lanthanum between the crystal and the melt. Or for example, concentration of lanthanum in the liquid by concentration of lanthanum in the solid. Or whatever that is, whether you invert it or not. It is this ratio. Now what happens? These trace elements, as they call it, they occur in very, very low concentrations in the rocks. So what happens when they are at very low concentrations in the rocks? That means their concentrations are tending to 0. If their concentrations are tending to 0, then the activity coefficient is equal to 1, tending to 1. This makes the mathematics of treating trace elements easy, because you don't have to handle the gamma value, which could be a very complex function if x did not tend to 0. If x did not tend to 0, then gamma will not tend to 1. I will show you in this diagram. You can see here. Say I draw a tangent here. Say I draw a tangent. A tangent. A tangent. What is the slope of the tangent? Is dy by dx. That means dA by dx, activity by composition. You can see the slope is changing. If the slope changes, that means A by x or gamma is changing. And it is this change is a function of the composition xi. So the minimum that you can expect for a non-ideal solution is that your gamma value is not constant. The gamma value is a function of composition. It could be a function of pressure, temperature, but definitely composition. So you can see, otherwise, if gamma value was a constant, you would never get these differences in slope. So essentially, in non-ideal solutions, gamma is a function of the composition. Have you understood? So if gamma is a function of the composition, then this will be very difficult to model because it becomes a function of composition. That is why this theory is taken to because of this reason. You take elements with very low concentration tending to 0, that means a gamma value tending to 1, and that's easier to handle because gamma is 1, then non-ideal solutions where gamma values are at least a function, definitely, of temperature and a complex function to add to it. And if gamma value is a complex function of composition, then activity also becomes a complex function of not only this, but also the gamma function. So activity for an ideal solution, that means gamma is equal to 1, is a linear function of composition. But for a non-ideal solution, activity is a non-linear function of composition. That is why people working in trace element geochemistry look for trace elements. Lower the concentration, better it is. Lower the concentration, better it is. Because you are approaching X tending to 0. Have you understood? So this is a few things that I wanted to tell you before we move into a little more complex things. But if you have any questions, as I have told you repeatedly, you can go through the books. If you still have questions, you can mail it to me and I will answer it for everybody. I don't answer individually because if you ask me a question and I ask you back, then the class does not understand. So I will say a student asked me this question and here is my answer to it. So the whole class knows what was the question and what was the answer, instead of me and you being very personal to each other. So I don't like this. The class as a whole, I understand. I don't want individuals. So I want to have the class as a whole. So we have learned quite a few things. One is called the system, one is called the phase, one is called the files component, one is called the system component. So we have understood a few things already to start with, to understand what lies ahead. These are the basic things. Remember, for an ideal solution, gamma is equal to 1. That means activity is a linear function of composition. For non-ideal solutions, gamma is not equal to 1 and gamma is a function of composition. So the activity is a non-linear function of the composition. At infinite dilution, activity tends to mole fraction, at infinite dilution, mole fraction tends to be 0. That means the activity coefficient tends to 1, and that is very easy way to handle trace element geochemistry. You will see major element geochemistry cannot be handled this way because of the strong non-ideal effect and the strong non-linear variation of activity with composition, of mole fractions, compositions. Okay, I think I will stop here because the thing that I have to start from here, I don't think I should be stopping in the middle. It's a little too boring. So let this class be a little curtailed. It does not matter. Next class we will try something different. Right? Thank you.